Defense. So these are my committee members. John and Elaine are the co-chairs, and then also Bobby and Larry Washington. Thanks there. So the way this will work is I'm going to give a talk for about 15 minutes, and after that you can ask questions. My committee can decide if they need to talk about anything ahead of time. Okay, so we'll begin with that, and then after about an hour when we're done with questions, then everyone else has to leave, and then the committee will grill me until they reach a decision. Okay. So my name is Andrew Miller. I'm going to be telling you about my dissertation work, which is called Provable Security for Cryptocurrencies. This work is really inspired by a recent and really interesting phenomenon, which is that for the first time over the past few years, we've seen a currency, a virtual currency, reach fairly widespread adoption that isn't run by any government or by any corporation. There are lots of virtual currencies, even like World of Warcraft Gold, but these are all run either by a company that's responsible for administrating it, or they're actually a state currency. And this was something that was created as a peer-to-peer network in 2009 by a pseudonymous figure called Satoshi Nakamoto, whose identity we still don't know. And since its launch in 2009, it has been traded on exchanges and has grown in value like other commodities and stocks. At the current time, it has a market cap of about $10 billion. Market cap's just the number of units that are in circulation times the current price, so this is kind of a measure of the economic significance. For comparison, this is comparable to the M2 money supply of the Guatemalan state currency, the Quetzal. So this is like all of the money in circulation plus the money in short-term bank accounts. As another point of comparison, if you look at the top 100 by market cap of stocks on the NASDAQ stock trading exchange, if you go down to about 100, you see companies whose stocks traded on NASDAQ are worth about $10 billion in market cap in total. A couple of examples of companies in that range are Mobileye and Juniper Networks, if that helps. So it's still nowhere near the size of like the dollar, but it's still really significant for such a strange network that has no administrators and is completely decentralized as this is. In addition to that, there has been a bunch of investment in technology companies related to Bitcoin that think that the technology underlying this is going to...
Sure. Move up one way or the other, you're blocking the screen.
This way?
Either that or the other way.
Or all the way. Okay.
Yeah.
So each one of these data points represents an announcement from either a financial services company or a financial technology company investing in blockchain technology, which probably is some kind of technology inspired by Bitcoin. The functionality provided by Bitcoin is like that of other virtual currencies. You can think of this as a simple application on top of a consensus system, and a consensus system is just a shared database that can be used by parties that don't trust each other in order to allow them to interact with each other. And in this case, the role of this database service is to store account balances for each account held by any of the users of the system. And the way that you interact with it is you can send a command that says transfer some of the money in your account to the account of someone else, and then the database is updated accordingly, and the person who receives it learns that they've got money. The virtual currency application is compelling because there are some really clear security properties that you would need. You care about database consistency because you don't want Alice to be able to spend the same money in 2 different places at the same time, or to create money that she doesn't have out of thin air. You care about availability. If you're going to pay for this for something, you don't want the service to not let you use your money. There's clearly some need for access controls. You don't want Bob to be able to spend Alice's money without her permission. And depending on the application, in some cases you may care about privacy. You don't want everyone seeing all of the transfers you make. Now, the justification for the security of a system like this traditionally is based on having the administrator who operates this virtual currency be responsible for maintaining the database. So it would be unsurprising if Facebook has a virtual currency and they're in charge of the computers that are implementing this. There's a really wide literature in distributed systems of how to build fault-tolerant and scalable systems like this. They all take the form of the following. So the administrator of the virtual currency, like Facebook, would set up a network of these different nodes. They would assign a public key to each of the nodes so that all of the nodes in this network know about each other and they can communicate over secure channels. And then you can run a variety of the algorithms that have been studied over the past couple of decades, a prototypical example of which is PBFT. And what these guarantee is that all of these servers can reach agreement on the state of the database, even if some small number of them get crashed or hacked into or fail in some way. However, this still relies inherently on having Facebook appoint all of these servers and designate them, and these algorithms generally assume that you have a fixed set of participants from the beginning. In the setting of Bitcoin, where there is no administrator and the system's supposed to run itself, anyone can come and join the network, and this is a lot more challenging of a setting. In particular, the main challenge that you run into is what's called the Sybil attack, which is where an attacker simply connects to the network with tens of thousands, hundreds of thousands of its own nodes or different IP addresses. All of the traditional algorithms that I mentioned, like PBFT, have a flavor of collecting votes, where at some point you poll all the servers and you only proceed once you receive a response back from a majority of them. But it doesn't work to collect votes if the attacker can stuff the ballot box. So this setting is so challenging that it wasn't thought that anything like a consistent database would be possible in this setting. Now, because Bitcoin has been the success for several years, it seems like maybe this is possible. The best argument that we have for the security of it is just the fact that it has been running with uninterrupted service for 7 or nearly 8 years now. Understanding the security of these systems is really important because, as I mentioned, now there are billions of dollars of market value at stake. On the other hand, these systems are very difficult to reason about their security for a few reasons. One is that the protocol isn't fixed, but is actually constantly evolving as developers update it and add more features to it. Bitcoin's the largest and the first of these, but there are actually hundreds of competitors that modify the protocol in some way and are trying to compete with it. And as I mentioned, the challenge here is that the structure of these protocols is actually significantly different than the body of work that I mentioned that is for a more restricted setting. So the approach that I take in my work is to build a provably secure cryptocurrency protocol. So this is a protocol that is a simplified and somewhat generalized version of the cryptocurrency systems that we see today. And I give precise statements about what their assumptions are, how the protocol works, and what its security guarantees are. This gives us the following 3 benefits. We can analyze the security of the existing systems by using this provable security of using this protocol model. We can also propose and validate new upgrades to the protocol and get a validation about their security. And we can also add new functionality on top of these so that we can use even more kinds of applications built on top of them. So I'm going to go in this talk and through these 3 parts. So I'm going to start by giving you a background on how Bitcoin works, and in particular how the Bitcoin mining protocol works. These systems are complicated, but it helps to understand them in layers, and I'm going to keep referring back to this layer diagram. At the bottom layer of a cryptocurrency network is a communication system, which allows any party in the network to publish a message. The messages are called transactions, and these messages get propagated to everyone else in the network. The middle layer, which is really the most core part, is a consensus protocol, and the goal of this is to allow everyone in the network to agree on a globally consistent ordering of all of these transaction messages that have been published. All right, and then finally, on top of this ordered transaction log, you define an application that imposes some semantic meaning to an ordered log of these transaction messages. Now, what's interesting and difficult, or what's really fundamentally novel about Bitcoin's approach is, first of all, for this lower layer of communication, it's an anonymous network. This is significantly weaker than the standard networking assumption that traditional distributed protocols are built on top of. And I'll mention more detail about how this is different. And the protocol that Bitcoin uses is a novel protocol that has a fairly different approach involving a lot of computational power. I'll describe these in a little more detail. Again, the key challenges in this space are that in the traditional world that we're familiar with, you have a fixed set of participants who know each other, and in this decentralized setting, anyone can join, and this means that Sybil attacks are a difficult problem to overcome. The second difficulty is that in the traditional world, you typically just assume that a majority of the participants in this fixed network just follow the protocol correctly. Whereas in an open system where anyone can join of their own volition, you might expect incentives to hold. So maybe people won't follow the protocol if they can profit by deviating from the protocol. Now, the main idea that Bitcoin uses to overcome these is really these 2 ideas. The first is that to defeat the Sybil attack, we're going to make participation really expensive by using computational puzzles. So you have to invest computational resources in order to participate. And the second main idea is that you get a reward for participating, so that's why people have an incentive to follow the protocol. Now, let me give you a brief description of how this protocol works specifically. So again, the functionality begins when someone wants to send a message, so Alice wants to transfer some money to Bob. The application layer isn't too complicated, just think of these as digitally signed messages. What I'm going to describe is the process by which the Bitcoin network agrees on an ordering of all of these transaction messages. So zooming in a little bit, the Bitcoin network consists of nodes called miners. And each miner is going to keep track of the entire log of committed transactions so far. Transactions are committed in batches called blocks. Each miner is also going to keep track of a buffer of new transactions that have been propagated in the lower layer messaging network, but haven't yet been committed. And what's going to happen is that each miner is going to try to commit a new batch of transactions by finding a solution to a computational puzzle. Now, the way this computational puzzle works is a solution is going to consist of a string, such that when you take the hash of this string, the hash, which is like a random value for any string you choose, has to fall within some narrow range, like having the first few hex digits, in this case, being 0. The structure of the solution is going to have 3 parts. The first part of the string is going to be a hash of the most recent block. So this is basically a hash of all of the transactions committed so far. The second part of the string is going to be the contents of that buffer of new pending transactions. And also here, note that the miner who is mining this is allowed to insert their own transaction, which pays them a bonus. Associated with the public key of their choice. This is what's going to provide the incentive for them to do this. All right, then the final step is you have some arbitrary string called the nonce that the miner can choose. And each time you choose one of these and compute the hash, you essentially have some chance of finding a valid puzzle solution. So the miner will, after fixing the first 2 parts of it, they'll try several times until they find a nonce such that this hash lies within this narrow range. All right, so this would be a winning puzzle solution. When a miner finds a puzzle solution, he adds it to his own local view, and he also broadcasts this puzzle solution on this that lower level communication network to all the rest of the nodes so that they can update their state accordingly. In Bitcoin, the difficulty of this puzzle is adjusted such that someone in the network finds a puzzle in expectation once every 10 minutes. All right, and at the current price, or at least at the price of a couple of weeks ago, and given the amount of the bonus in each block, this works out to $1 million per day in rewards that the Bitcoin network is given to the miner nodes that are participating in this way. $1 million per day in total. What does $1 million per day of incentive get you? Actually, this is enough money that there's a whole industry that's arisen just for the sake of Bitcoin mining. So this is a picture from as far back as 2014, so there are more sophisticated ones now, but all of these are Bitcoin mining equipment, and this one Bitcoin mining company, KNC's data center. So there are many different racks, and each rack contains specialized Bitcoin mining ASICs, which are specific circuits that are designed and manufactured just for the purpose of Bitcoin mining, no other purpose. All right, so that's what $1 million per day, in a sense, encourages to grow around this system. The first part of my dissertation is actually the first security proof that this Bitcoin consensus protocol is secure. And this proof is under the assumption that a majority of the nodes in the network, weighted by their computational power that they contribute, are following the protocol correctly. And I want to just give a couple of details about the assumptions and guarantees that go into this proof. I'm not going to go into too much detail. At the low level, again, the communication network is weaker than the traditional setting. We assume that when anyone publishes a message, it gets delivered to everyone else within a fixed amount of time delta, which the protocol depends on, so this is a synchronous network. The key thing is that it's anonymous in the sense that when you receive a message, there's no indication of who it's from. So there isn't any notion of identities, and this network doesn't guarantee that a particular person sent any particular message. And this is what makes this assumption more challenging. In terms of defining the protocol, what I prove is actually a simpler form of Bitcoin that isn't actually continuously adding on transactions to the log. Instead, I simply look at a one-shot consensus, which means that every node in the network begins with some input, and the goal is going to be to, after some finite time, reach agreement on one of those input values, and it should be one of the honest parties' input values with some sufficient probability. And this is simpler, but the intuition is you could run this sequentially many times and then have a better approximation of an ongoing service. Instead of simply proving this for the specific puzzle that I gave you the illustration of, we actually prove that this is secure for a more generalized puzzle that's called a scratch-off puzzle, which satisfies a couple of these properties, which essentially mean that the intuition is that it isn't too much different than the puzzle mentioned before, in the sense that the only effective way to approach it is to make these random brute force guesses. So the attacker is forced to make random brute force guesses, and in particular, all of the honest parties don't have to coordinate. they all just look through a different area of the solution space, and they're all effectively collaborating to solve the puzzle together. So, you know, twice as many people, even if they're operating independently, solve the puzzle on average twice as fast. To give just a quick, yes?
You made this comment about roughly 10 minutes, but if you have increasing numbers of participation and it's essentially a parallel search, does the protocol somehow?
That's true. The protocol has an auto-update mechanism, and in fact, it's always been faster than 10 minutes because it is always increasing, and so it's always catching up a little bit. Throughout my protocol, I don't model anything that involves the auto-update procedure, so I assume that there's a fixed power, but that is a realistic thing that the systems do have.
What was your 16 to the minus 3?
That is just a hypothetical number for that experiment. That's
okay.
Just because I had 3 hexes.
It's
actually way more than that. It's
okay,
like
okay.
70 bits.
Okay.
Which is like a desk crack every 10 minutes or something like that. It's a really huge amount of computation. So I'm just going to describe the sketch for the agreement proof, which is the key part of this. What happens is if I want to prove that, let's say that X is the number of among all of the miners in this network at some point. X is the minimum number of puzzle solutions in a chain, blocks building one on top of each other that a miner knows. In order for there to be a disagreement, because the protocol says that miners will always be building on top of the longest such chain of puzzle solutions that they know, in order for there to be a disagreement about the transactions in the first block, there would have to be some other miner in the system that has a different puzzle chain, that has different puzzle solutions at each step that is at least as long as X. So to prove that this doesn't occur, assuming that the majority of the miners by their hash power are following the protocol, what I do is establish 2 randomized bounds. The first one is going to be a bound for how long it takes miner among the nodes who are following the protocol to get X puzzle solutions. And because this reduces to this brute force computation, and we assume that each little step of the computation is very small, we can model this as a Poisson arrival process. So the time between puzzle solutions is an exponential distribution with this parameter mu b, which represents the CPU power of the nodes following the protocol in the network. And when one of them finds a puzzle solution, they broadcast it, and so after delta time, everyone in the network is going to have a chain of puzzle solutions at least X long. I then provide a second bound, which is for the rate at which the network overall, including the attacker, and allowing the attacker to not even have to worry about the message delay. It doesn't have that extra delta added on, and it has a different parameter mu, which we assume is less than 2 mu b. And by comparing these 2 exponential distributions under suitable assumptions about mu and ud, what we can prove is that with high probability, there's some time r hat, which we choose, and some number of puzzle solutions x, such that the honest nodes in the network know a chain of puzzle solutions that's at least x long by time r hat, and the network as a whole does not yet have 2x puzzle solutions in total at time r. And that excludes the possibility of this case occurring, which is what ensures agreement. Yes?
So this proof, does it work if it's like a partially synchronous model?
No, what's critical is that we have to show how to choose the puzzle difficulty so that it's effective. So that the puzzles arrive not too quickly, because it's important for this bound to hold that the puzzle solutions are found such that they can propagate before someone else finds a puzzle solution.
Do you assume
so we essentially have to know what delta is in order to do that. And in practice, the Bitcoin network needs to have these hard-coded parameters like 10 minutes.
Yeah, but do you assume the protocol waits for delta as a synchronous
It
round?
doesn't wait for delta.
So the proof still holds if the protocol, the nodes don't wait for delta as a synchronous round?
Yeah. I know that we've had a disagreement recently about what the definition of partially synchronous is. So my version of that would be that you don't know what delta is, but the protocol doesn't wait for delta, but it does require delta to be known.
The proof doesn't have to deal with selfish mining attacks?
This proof includes selfish mining attacks because these bounds are so broad that they include anything that the attacker can do, including a selfish mining attack. A selfish mining attack is a well-publicized attack on the mining algorithm that doesn't violate the consensus properties, which are the only ones that I'm aiming to prove, but it does undermine an additional property that you would like, which is that you're guaranteed to get a proportional amount of reward. And miners can overcome that. If you have like 45% of the hash power, you could get maybe 50% of the rewards, and everyone else would get a little bit less. But that's not included in what I'm claiming. But this does account for those attacks.
So how big is delta in practice?
There's a measurement is 10 seconds.
Yeah, wait, what?
According to Christine Decker's, the measurement is about 10 seconds.
Yeah, we do measurements,
Is that to
there's
reach,
several
is
people
that
who
to
do
reach the
measurements
whole
on the
network or
network.
to reach some friends?
I think 90% or something.
Yeah.
And so you never have two people come up with the same coin?
No, they absolutely do. They may come up with that at the same time.
Okay.
That wouldn't show up as, yeah. I mean, that doesn't show up directly in this model. That can happen. The fact that the delta is present there does compensate for that. And that's the intuition for why you can't just have, why there has to be some constraint on how difficult the puzzle is. If the puzzle were very easy, millisecond, then everyone would find a puzzle solution.
Actually, that's a really good point though, because if you, I mean, I'm not sure, maybe you treat it more formally in the thesis, but you need not only X puzzle solutions, you need them actually to be bound to each other in the chain structure.
This is the length of the longest chain.
Okay.
So
Because if you found two of them at once, they would be divergent chains, and
That's
only
true.
one would chosen. Yeah.
that's true, but that's what the delta is for.
No, but delta doesn't account for that. I don't think.
It does because
Why doesn't your exponential give you answers less than delta with
it does.
The
You can think of, one way to think of this is alternating phases. So I go until I find a puzzle solution, and then I'm going to weight delta, ignoring any puzzle solutions that might be found during that time.
Yeah, but correct processes may not be mining off the same fork, right?
That's true, but they will. But I mean, by definition, they will be mining on something that's at least x by the time that they get that plus 1. In other words, you can think of if I laid these out, then I would have these alternating phases of finding a puzzle solution and waiting for the last solution to arrive in this stochastic model. But actually, nodes would be finding puzzle solutions during that delta wait, but I'm just not counting them. So this still does serve as a lower bound for the rate at which the on-disk nodes extend the length of the chains that they have.
This is assumed, like if they have, you have some assumptions, right? In the protocol, if they have equal length chains, and they'll pick.
I have to assume that they start off with, that they start off at some well-defined point, all with 0.
Mhm. Okay, yeah, maybe I can take a look.
What is it, BX? BX is the
Bx is the time at which all of the nodes have a puzzle chain that's at least x long. So the x is always a number of chains, and the value of these random variables is a time. Okay. So this is the first proof of security about this protocol. In the original Bitcoin white paper, there was a little argument that addressed a single kind of attack. It specifically said that an attacker who works by going to some point in history and trying to build a new fork from that point, that particular attack won't succeed. This was the first proof that applies to any arbitrary attacker, not just to an attacker that follows a particular strategy.
So can you comment about how this relates to the backbone protocol paper from Eurocrypt?
Yeah, so, and I should have also mentioned that this model of the anonymous broadcast network, that model has been subsequently used by several other works, including the backbone paper and Rafael Pass's recent paper as the basic assumption. The backbone paper is, the main difference is that while this just models this one-shot consensus, the backbone paper actually models the whole ongoing thing. And you can simply run this sequentially and thereby get an ongoing service, but it's not as realistic to what Bitcoin actually does, and it's not as efficient. So the subsequent crypto paper is a closer model to what Bitcoin actually does.
But their analysis, I mean, it's true that they're a more general model, but somehow their analysis is much more complicated than what you have on this slide. I'm wondering why.
So
I mean, is it because of that?
They were, I think they spent most of their time dealing with the selfish mining attack. That's why, like, I was asking.
Yeah, they prove a stronger bound on the selfish mining thing, which is part of it.
Okay.
But the reason why you don't have to deal with that is because.
Well, I guess he's proving a weaker statement.
I'm proving, yeah.
But even if you just broadcast, you don't have to deal with selfish mining. Is it because, like, so you assume if they if the honest nodes have equal length chains, they pick the same.
This is consensus, right? It's the same X chain, right?
This is just the number, so it doesn't have to be the same, but if this condition holds, then it must be the same, at least in the first block.
So, sorry, doesn't the selfish mining thing say that you only need a third to?
You need a third to start getting disproportionate amounts of profit. In other words, this will guarantee that you reach agreement, but it may be the case that the chain that you reach agreement on disproportionately contains attacker's blocks, which would give the attacker more reward. But the selfish mining attack doesn't undermine any of the consensus properties, just an economic property. Okay, so I'll move on. What I'm going to talk about next, I mentioned that we proved this consensus protocol result for arbitrary scratch-off puzzles for this class of puzzles that I've defined. What I'm going to talk about now is how to upgrade the protocol to have extra benefits by instantiating the Nakamoto consensus protocol with different scratch-off puzzles. The first thing I'm going to do is to explain how to do this instantiated with a different puzzle scheme in order to address one major problem facing Bitcoin, which is the problem of mining coalitions. So most miners in the Bitcoin network don't participate as independent individuals. They actually pool their resources in these coalitions called pools. This involves deviating from the protocol because the nodes in the protocol aren't doing the work that the protocol says. They're essentially taking orders from the central pool operator. And this produces a risk because you may be able to compromise a large portion of the computational power if you can compromise whoever is controlling one of these coalitions. So a typical mining pool looks like this, where you have a bunch of miners who are participating, but they're taking instructions from a pool operator who says what transactions they should be trying to include and which block they should be trying to extend. When one of them finds a solution, they effectively send the reward to the pool operator, and then the pool operator is responsible for divvying up the rewards to all of the miners. Now, throughout Bitcoin's history, there have been a very small number of mining pools that have accounted for the vast majority of the mining power. And in particular, in summer 2014, one large mining pool, ghash.io, accounted for over half of the network's hash power on its own, which immediately undermines the assumption under which we can prove it's secure. This led to a huge public outcry, and there was a convening in London of miners, and they all essentially agreed to limit the hash power of any pool. There's also like an unknown range, so even though they may say we're not going to have that much hash power under our control, it's hard to even guarantee that they're doing that. So you can think of this as actually a breakdown of one of Bitcoin's kind of key ideas, which is that we want to have an incentive structure that encourages participation that keeps the protocol secure. So we want a robust and trustworthy system. We're going to achieve that by having a highly decentralized network. And it's going to be decentralized because we have these incentives that make it decentralized. But the fact that these coalitions form is a breakdown in the incentive structure that we can try to fix. There's the key observation, which is that the reason that pools can grow so large is that the members of the pool don't even have to trust each other. Instead, the pool operator is able to have the miners produce these incremental proofs called shares, which essentially prove to the pool operator that the miners are doing work that, if it was successful, would pay out to the pool operator's public key. So there's no way for the members of the pool to take the reward for themselves. Just to give a little description of how this portion of how that proof works, what you essentially do is have each miner submit these partial proofs of work called shares, which have an easier to hit target than the Bitcoin puzzle. So if it takes 6 hex digits to have a Bitcoin solution, to get a share of a mining pool, you just have to show that you have 2 digits of 0. So it's an easy target. But you have to have a puzzle solution that has the transactions that you're committing have to include the payout to the pool operator's public key, which means that you can't reuse this work for yourself in order to pay out to anything else. So the transactions must be the ones chosen by the pool operator. And again, you just do the ordinary mining work, but you find a share of a puzzle solution. When you have that, you submit it to the miner, and then the miner will, when it finds a real puzzle solution, the mining pool will share the reward in proportion to how many of these partial proofs of work you've given out. So my solution to fix this is going to be to modify the Bitcoin scratch-off puzzle to a new puzzle that is going to make it so that the miners that are members of a pool would have the mechanism and the incentive to defect and take the reward for themselves. The key idea here is that I'm going to do this in 2 steps. I'm going to make it so that to be a miner in a pool, you have to know a secret key. In order to do any proof of work mining, you have to know one of these secret keys. And if you know a secret key corresponding to a solution that's found, you can use that secret key to take the reward for yourself by defecting from the pool. The way that I'm going to do this is going to involve modifying the puzzle construction in 2 steps. So the first is I'm going to modify the puzzle construction so that you need the secret key to do the work. So this was the original Bitcoin puzzle structure. I'm now going to add 2 elements to the solution string. It's going to be a public key, and it's got to be a signature S1 under the corresponding secret key to PK. And this signature has the form of being a signature over the remaining parts of the solution string, the previous block and the nonce. In order to do this puzzle solution, you would then pick a possible nonce, and then you would compute the signature, and then you would compute the hash, and only then see if you won. Right, and then the verification condition is also extended to include the signature. And the second step is to make it so that if you know the secret key, then you can take the reward for yourself. And I do that by removing the transactions that you're committing from what you compute the hash over, and instead add a second signature where you assign to choose which transactions to include. So the idea is that you pick your previous block and your nonce, you compute one signature over that, then you take the hash and see if you found a puzzle solution. And if you do have a puzzle solution, then you make a second signature using that secret key in order to choose which transactions you're going to commit. So now you have to know the secret key in order to do effective work, and if you know the secret key, you can take the reward for yourself. This is actually a really counterintuitive protocol, so I just want to try to explain it and give another angle of it. It's counterintuitive because normally we just try to design secure protocols against an attacker. Here what we're actually trying to do is to prevent a secure protocol from existing. The reason is we don't want parties to follow the secure protocol if it's a deviation of the protocol we want them to follow, because that might lead to systemic risk. And a helpful analogy, if you're familiar with e-voting at all, there's a concern in voting schemes called vote buying, where you don't want people to be able to sell their votes for a profit to someone who wants to buy up a lot of votes. So it's considered a virtue of an e-voting scheme if it has coercion resistance features, in the sense that you can't prove how you voted, which prevents you from being able to stand outside a polling booth and prove to an attacker how you voted. So similarly, it's trying to prevent a deviating protocol. Essentially what non-outsourceable puzzles are is like coercion resistance, but for Bitcoin mining rather than for voting. Since originally announcing this and publishing this for the community, this idea of non-outsourceable puzzles in our construction has been used by some altcoins that are Bitcoin competitors, such as Ziftercoin and Spreadcoin, that can promote having better decentralization as one of their competing features.
How do you get consensus on which transactions are in the block for which you have found?
Yeah, so what happens is that you're getting agreement on the previous block, because this previous block includes both the puzzle solution and the signed set of messages.
Because
So you're always
the
lagging
guy,
one
the one
behind.
who found this can publish 2 different transaction sets.
That's true, yes. But regardless, the network, there's no guarantee ever that the network is agreeing on the most recent block. And this effectively adds 1 block of extra uncertainty, but the convergence still holds.
So in your broadcast protocol, how are you deciding the bit to output in the end, in the first part?
It's the transaction in the first block.
In the first block?
Yeah.
Mm-hmm.
Also the definition of the scratch-off puzzle, I'm not going into the details, but has to be really carefully worded to make it so that the fact that you can add these extra different transactions if you find one puzzle solution doesn't, that isn't a violation of that.
Well, I mean, you can choose any subset after you find them.
After you find it, right. But if you don't reveal any of those and you found it, you're not helping an attacker find any others. The attacker can't change the message if he doesn't see your key. So that was one example of a different scratch-off puzzle that has some beneficial effect. In the paper for this, we also have a stronger version of non-outsourceable puzzles, which avoids this problem. We provide the mechanism to take the reward, but you might leave an incriminating trail, which leaves open the option that a mining pool might make you sign a legal contract ahead of time or deposit some escrow collateral. And so a strong non-outsourceable puzzle has an extra layer of cryptography that makes it so that you can defect from the pool and hide your track so that no one will be able to incriminate you. And a second form of this that I won't go into, but is in my thesis, is a storage-based puzzle. And here the idea is that in order to do mining, you have to be storing some useful data set, like a portion of a data archive of some public interest, like a Library of Congress archive or internet backup. And the key idea is that we build a puzzle that satisfies all of the requirements for the original proof to go through, but it's based on a proof of retrievability. So the only way to solve the puzzle is to store a portion of some particular data set. This one in particular because it reduces the waste in Bitcoin by getting a secondary purpose for the same investment in mining resources. This idea resonated with a lot of people, so this was featured in Scientific American Nature magazine. Okay, I'm going to move on to then, now assuming that we already have a consensus system, I'm going to talk about the applications that we can build on top of it. IBM recently released a vision paper where they suggested that all of the fun buzzword topics of the year, like Internet of Things and self-driving cars and that sort of thing, might all be able to benefit by having a universal digital database like that of Bitcoin, where you could put on access control lists or in some way serve as a kind of coordination point for all of these different emerging systems that have varying kinds of trust concerns and different people in administrative control over it. The key idea here is that even though I started by saying this is a virtual currency system and Bitcoin is a virtual currency system, what you could think of is virtual currency as just one application that runs on top of a consensus protocol. You can think of a more general model where instead of just running virtual currency, you have arbitrary programs that each have their own code defining them, and they have storage resources like an ordinary computer, but they're all being executed jointly by the network. And so we call this, in general, the blockchain model, and I'm going to call any program that runs on such a blockchain a smart contract. It's not a legal contract, so don't get stuck on that word, but that's just a historically chosen name for programs running on a decentralized consensus system like this. And now users can interact with these programs, these smart contracts running on the blockchain. They can also send application-specific data as well as money too. This idea was really popularized recently by one of Bitcoin's top competitors right now, Ethereum, which introduced a programming language and a blockchain that runs arbitrary user-defined programs, and they have this vision of an app store where anyone can develop their own applications to run on top of a blockchain. You can implement things ranging from crowdfund campaigns to auctions and elections and all sorts of new things. And these would all be running on top of a blockchain and people could use them. Ethereum is doing quite well. Right now they have been, I think their 1.0 release was less than a year ago, just a few months ago. They already have processed over 7 million transactions, and there are almost 100,000 instances of these user-defined programs running on their blockchain. Right now their market cap is $1 billion, so this is like a tenth of that of Bitcoin. But still this is the number 2 in, by this measure, cryptocurrency today. One of the big concerns with the programs running on the Ethereum blockchain is privacy. So by default, everyone in the network sees all of the transactions from the moment they're broadcast, even on that lowest level of the network. So in this case, it means that all of the code of the contracts you write is public for anyone to see. All of the data you send to these processes is public, and all the money transfers you send is public. Depending on the application, this can be important privacy leakage. So if you're trying to simulate a stock market on top of Ethereum, you reveal what stocks you're interested in. If you have insurance smart contracts, then you're revealing which risks you're concerned about. And because an attacker can see the messages right when they're sent on the network, not even before they are committed into a transaction log, an attacker can effectively front run an order. If you want to have something like a market book, the attacker could insert his own transactions that get committed before yours do, even if the attacker saw yours. As an example, this is what would happen if you tried to write a sealed bid auction directly on top of Ethereum following their standard documentation. You might make a contract that has the rules of a second price auction written in simple language, and users would submit their bids up until some deadline, and then after all the bids are in, the smart contract would say how to assign the second price to the winner and give a refund to everyone else. But again, the problem is that every time a user makes a bid, it's immediately visible to the blockchain and everyone on the network, including the attacker. In particular, the attacker could front run your bid in the auction and wait to see what everyone else's bids were before making his own. Now, a naive attempt to improve this might be you might try to do some kind of encryption and send an encryption of the amount of money you're bidding rather than the money itself. Now you have the problem that the smart contract program, since it's just run by the public, can't compute directly over the ciphertexts.
By the way, I thought the whole point of the second price auction was that it doesn't matter if you front run.
I don't believe that's true. I mean, you don't have an incentive to...
Even if you know all the other bids, you don't have an incentive to bid anything other than your valuation.
I don't believe that's true. You
No,
can see
that's
what the
true.
other...
That's the property of the second price contract. If we don't have incentive to over or underbid.
even if you get to see all of the other bids before.
Yeah.
Why is it called sealed bid?
I mean, maybe a sealed bid, I think usually means something different.
I don't have,
No, I don't think so. You can just bid a little bit higher than the highest bid, right?
You can work it out, I mean, it's a nice equilibrium to bid your valuation, regardless
you
of the
get-
bids of the other players.
even if you get to go last.
I mean, well, actually, let me save you here, because if you have two bidders working in collusion who can both front run, then you can subvert the protocol.
I see.
But with one,
Yeah,
it's-
that's probably
it's-
why. Looking ahead where I'm gonna go, then to just avoid having that be a lingering thing, what we're eventually gonna look towards guaranteeing that even after the fact, all of the bids remain private to, each party learns its own bids, but not the bids of the other parties, and if no one wins, no one learns what the bids were. No one except the winner even learns what the final price was. Another obvious choice might be to have a third party that you send all of the money to, but now you've introduced a third party, and the third party could just run away with the money themselves. So what we do is build a system called Hawk, which is a framework for privacy preserving applications, including auctions like that. And the main idea here is that we're going to use zero knowledge proofs in order to, these are crypto schemes that allow you to prove statements about some ciphertext without revealing any other information about the plain text underneath. In the Hawk form of a blockchain auction, what you do is have some public parameters associated with the zero knowledge proof scheme put into the public blockchain. And the users are now going to send a commitment, which is just like an encryption that you can later reveal. They send an encryption of their bid along with a proof that says that they actually have the corresponding amount of money. We are going to introduce a semi-trusted third party I'll mention more about later, and after all of the bids are in, each party reveals what their bid was to the manager. And then finally, the manager is going to compute the auction function and make an encryption of the outputs to each of the parties, along with a final zero knowledge proof that says that he ran the auction function correctly and made the encryptions correctly to the keys of the parties that were involved. Since I introduced this extra party, you should be really suspicious about this third party manager, and so what I need to do is be really precise about what the guarantees are. You don't need to rely on the manager for correctness, because he produces the zero knowledge proof that says that he ran the function correctly. He didn't run a different function. Even the manager can't front run in the auction because he doesn't see what any of the bids were until all of the bids were committed to. And finally, this is built on top of an eCash system, and so even the manager can't undermine anything about the security or conservation of money in the underlying eCash system. The only thing the manager can do is reveal what the bids were, the inputs were of the parties after the contract has run. All right, and you can think of this manager as also just a logical role, so we could implement this with trusted hardware or multi-party computation, but it would incur an extra cost versus just running it as an actual single machine run by a party.
So who would be the trusted party in practice?
Do you
Do you think it would be a company, or what would it be?
Yeah, I could imagine a company doing it, or some trusted neutral party or something maybe. University lab, I don't know.
Which university?
Is the number of bids necessary to be known ahead of time?
A bound on the upper, like an upper bound on the number is because to produce the
So how does
knowledge
the
proofs requires that.
trustee know when it's done and can compute it?
What, sorry, what? Oh, that's based on timing, so we do have the time thresholds, and so there's a time when all the bids have to be in, and if they're not all filled up, then you don't include those.
Can you go back, because I'm just want to make sure I understand, one minute. Yeah, so I mean, the contract would be, I mean, what would the actual contract be? The contract would be looking at the public actions of the trusted manager?
Yeah, but the public actions, all you would see is at the beginning, you see, the public sees a bunch of commitments. At the end, it sees a bunch of further commitments from the manager along with the zero knowledge proof. And the logic of that zero knowledge proof says that these are the encryptions of decrypting all of the committed inputs and then running the algorithm.
But then what do you do with the final encryption? I mean, you never open that, right?
These are encryptions to each of the parties.
Oh, okay.
So each party gets their own package
And then
of
do you deal with
keys.
with things like, if one of the bidders aborts after the fact?
Right, so we have a way of handling aborting. Aborting is just when a party runs away, and doesn't send a message when they're supposed to. And if you don't send a message when you're supposed to, that's visible on the public, from the public information. So what we require is everyone puts in a collateral deposit ahead of time. And in particular, the manager puts in a collateral deposit commensurate with maybe the maximum that any party might get. So someone with, a lot of initial capital might be a manager in that case.
So I mean, in particular, you can distinguish between an abort by a bidder and the manager failing to include somebody.
Correct. You can tell if the manager doesn't include someone. So instead of just implementing this as an auction, what we did is build a framework where you can have arbitrary applications. So an application developer can write the logic for their private contract in a programming language, and we have a compiler called Hawk, which generates the cryptographic protocol implementing that application. So in addition to the auction, which is then just about 20 lines of code and roughly a subset of C, we also have examples of a small gambling game, rock, paper, scissors, a crowdfunding campaign like Kickstarter that refunds everyone if it doesn't reach a threshold amount, and a really simple financial derivative that lets you bet on the price of the stock. In terms of our formalism, what we do is essentially build a couple classes of kinds of applications, transparent smart contracts and private smart contracts. The idea is that transparent smart contracts are what you could run on Ethereum, for example. You can implement these directly on a consensus protocol. It guarantees that your messages are processed, but it reveals them to the adversary, and it can't have any private state. But we also define a class of private smart contracts, which can have private state. All of these are modeled in the UC crypto framework. The only thing that matters for that is that we describe what these are supposed to do by writing code, which, if it were code that was run by a trusted third party, it would implement the functionality that we want.
So why do you need Hawk for transparent contracts?
You don't need Hawk for transparent contracts. This is what we prove directly on top of the consensus protocol, and then we prove that you can implement a class of smart contracts, which is the class of contracts that Hawk can handle. You can implement those by building them out of a transparent smart contract.
So what is the class and how is it different or smaller than transparent?
It's a class that's parameterized by a user function, which is just a mapping from up to n inputs for some n of user inputs to user outputs.
So can any transparent smart contract be made into a private?
No, no. Not in general. All we do is that for a class of private smart contracts that have this, they're parameterized by this function, and they do what that structure is, like they collect commitments to inputs at some time, and then after that time they reveal them to a manager and then wait for the manager to go ahead, and then at the end they give the private outputs to each party. We can realize that class of applications.
Can you do applications in which there is more than one round of communication between the parties?
Not in what I've covered. That would be a straightforward extension. I say straightforward. That would be a good future work extension.
Because that seems like the first thing you couldn't do, like what you're saying, commitment, run, decommit.
Yeah, that's the only.
That's only a one round, one shot
Correct.
exchange. Okay.
Just to follow up on Bobby's question, it sounded like you're saying that contracts that are private are ones that perform the steps that you mentioned earlier, that do the commitments and everything else. Couldn't you compile a transparent contract to do those steps as inserted by the compiler?
So, sorry, say it again. If you could break this into a sequence of steps.
I'm saying that I thought your answer to Bobby was, if I'm given an arbitrary smart contract, which I'm thinking, an interesting thing about the contract is the function that I'm going to run. It takes a bunch of inputs and then produces an output, and the inputs come from each party. And you said, well, no, not everyone can be, every transparent one can be private because they don't necessarily send commitments and do this encryption step and everything else. But I'm saying, why can't you compile all that work in from an arbitrary?
That's not the problem, right?
So what is the problem?
The problem is that the structure has to be input, compute,
Yeah.
output.
Exactly.
Right? The commitment is just the way to provide the
I see.
input.
Transparent
That's why I was
contracts are-
asking if it was input, compute, and then further input based upon the compute, for instance.
I see, so
But
that
then that
can be
wouldn't be
transparent,
captured.
but it can't be private.
Well, at least not by the structure that it has.
I see.
So one way of thinking of this generalization is that our final model includes not just Bitcoin, but also Ethereum and Zero Cash, which is a private transfers, but no programmability. It's just you can send private money to someone else. These are two of the leading proposals for state-of-the-art cryptocurrencies. Our model generalizes all of these, and then it also provides a new data point because it provides both privacy-preserving payments and this kind of programmability that Ethereum does.
So just by the last discussion, you have Hawk too far down. Should it also be, is it also too far right?
Yeah, I see what you're saying. We do provide a model of what the privacy preserved in payments is. It is not exactly what Zero Cash provides, but it's equally private. Zero Cash has an extra feature which allows you to have long-term private keys. So you can send a message to someone by their public key without even having to talk with them out of band to like generate a new key pair for them. And so you can approximate what Zero Cash does, but it requires extra interaction. So yeah, technically it's too far right because there's a tiny thing that you can do with Zero Cash that requires extra interaction or protocol.
But if you just wanted private payments and Hawk, still need a trusted manager or no?
No, you don't need a trusted manager for payments.
You never need the trusted manager, right? You could just do multi-party computation on all of the people who are doing it. This is just a,
If you want payments, and the payments are gonna, you don't want, even if all of the parties to the contract go bad, you don't want them to be able to inflate money.
Well, I guess let me rephrase the question then. So without MPC, do you need the trusted manager for private payments only?
You don't need the trusted manager for privacy payments, no. If you don't try to use the contract feature of collecting lots of inputs and moving lots of outputs, then it just reduces to Zero Cash.
then that's just a commitment.
Huh?
That's just a privacy hiding commitment or something?
Yeah, plus a zero knowledge proof.
Well, I guess the
that it's-
payer would act as a manager or something like that?
You can do that too, sure. We include a formal model of Zero Cash and then build on top of that with extra functionality. So it's not like you have to kind of shoehorn it into rounds of the protocol, you just use the extra points that are just like transfer messages.
So coming back to Bobby's question about reactive functionalities, could you just take the output of the manager as you will take it normally and just, do another commitment on the next input and like run it sequentially what you did like?
I think that would be an effective way to do it, yeah.
Okay.
I think it's straightforward, that's kind of, the approach.
So this is how we probably do it?
Yes.
Okay.
Have the manager keep commitments to kind of increment this. Let me mention a bit about the implementation that we did of this. So I say that we created this programming language, but it's a little simpler than that sounds. We used an existing tool called Pinocchio, which takes C code and generates an arithmetic circuit implementing that C function. Arithmetic circuits are the native underlying language for existing zero knowledge proof systems. So this output of this compiler represents the user-defined portion of the application. All right, the next step is to extend the user-defined application with this extra layer of cryptography implementing the protocol. And let me at this point say that all of the work done to make this protocol as efficient was entirely done by Ahmed, and this required a ton of really good engineering and inventive stuff. So we need to include an encryption scheme and commitments and pseudo-random functions and other cryptography. And in order for these to be efficient when implemented as a zero-knowledge proof, you need to have crypto schemes that are efficient when they're implemented as an arithmetic circuit. And so in the Oakland paper, we have an efficient particular instantiation of all of these. Also, Ahmed has a later work that's currently in submission. I guess we'll hear back about that in a few days. But that includes a systematic exploration of lots of different potential concrete instantiations and benchmarks of how efficient they are. So I want to be clear that I'm not taking credit in my dissertation for any of the concrete details of the protocol or what make it efficient. Just the formalism and proofs about that. Finally, after having this augmented circuit, the final circuit that includes our protocol-specific things as well as the user application is fed as input to libsmart, which is an existing library for generic zero-knowledge proofs that's really practical. And just to summarize what our performance figures with this, in our test example of 100 users in an auction, the cost of this for the manager to do that last step is only 3 minutes. This is across 4 cores in parallel. And for a user part, this is also scales linearly with the number of users. For the users to do their initial zero knowledge input when they do their commitments only takes 50 seconds on a single core. And that work is independent of the number of users that are doing it. The main overhead in this protocol is just producing these zero knowledge proofs. There is other crypto in the protocol, but it has a negligible impact on performance. And probably the most important factor is what would be the cost of validating all of these zero knowledge proofs, because this is something that would have to be carried out by all of the nodes on the underlying cryptocurrency network that's implementing this. And for all the zero knowledge proofs in the protocol, it takes 1.5 seconds to verify them all.
Would you do better here by using tailored protocols instead of generic ones?
Yes, I believe that we would be able to use a tailored protocol to an application. That would be then a lot more efficient rather than using this generic. Because we're building the contracts on, sorry?
I thought I read something which said tailored protocols don't do better. I was thinking.
Yeah.
Eventually they don't.
Eventually,
Depends on the application.
in special cases, there are.
No, I mean,
special
50
cases.
seconds looks high when you could do a zero knowledge proof with all the mile commitments, you know, in a second.
Sure, so again, we're building on top of an underlying
No,
scheme
I
of zero cache,
understand.
and we could tailor a particular application and a particular eCache application, eCache protocol for that one application. But I think that having a one eCache and then all of these applications on top, I think.
I mean, 50
don't see
seconds
how
seems
we
long
would
to me, but I mean, I understand the benefit of having a generic solution, but if
Yeah.
but if auctions became popular all of a sudden, you might want to rewrite it.
A really popular place for doing auctions is like bidding in real time on which company gets to display an ad in your browser, and like you can't do that if it takes 50
Yeah.
seconds. So yeah, it depends on the application whether or not this is tolerable. Okay, so let me wrap up. So in summary, what I've done is build a model cryptocurrency protocol where I can say what the guarantees and assumptions are from the whole stack, beginning with a model of the underlying communication network through the consensus protocol and then the application layer. For the consensus protocol, I factored out this key primitive of scratch-off puzzles, one instance of which is embodied in Bitcoin, but then I showed how to make other instantiations of it that have these extra benefits. And then finally, I showed how to, instead of just having a digital currency application, to generalize it to a larger class of applications, and in particular provide protocols for new privacy-preserving applications that extend past what you could previously do with cryptocurrencies. I have done a bunch of work, especially in collaboration with other people, during the time that I've been here that I didn't include in my thesis. Broadly, these cover into a couple of categories. One of these is systems side. I've done some of this with Bobby, including measurements and simulations of the actual cryptocurrency systems today, and scalability issues with them. Also with Mike, I've done work on programming languages and cryptography to make it easier to build crypto protocols, and other issues about security when doing Ethereum-style smart contracts. And I've also had a really good time working with folks at Princeton and building an online course, and my textbook is now on Amazon, so you can buy this. There's also a free PDF, so you don't need to buy it unless the book turned out really well, so that's why I'm showing it off. The overarching question that I'm trying to address, this work is really just the beginning because I'm able to show some kinds of improvements and provide some structure for some kinds of applications, but there's a lot more that we would like to do. So in general, the question that's motivating me is, can we design secure public infrastructure systems that anyone can use for as broad classes of applications as we can, and even under really difficult environments where you don't assume that you just have a trusted administrator in charge of everything. And so this is the overarching question that I'm going to begin working on when I start as an assistant professor at University of Illinois in the Security and Privacy Lab this fall. Okay.
Assuming everything goes well.
Assuming everything goes well today or shortly after today, but found the time. Okay, so I'd like to thank all the people that I've worked with over the few years here, and I'm done. Thank you all.
Any questions from the audience?
Yeah.
Is there any ability for Ethereum or Zero Cash to adopt some of the lessons you displayed today into their?
It's really difficult to upgrade Bitcoin, especially with experimental stuff, because there's so much money at stake that people are justifiably very concerned. I should point out that Greg works at Blockstream and is a UMD alum, so he works for one of the companies that is most in charge of upgrading Bitcoin development. So you're welcome to
We'll work with smart people.
You work with smart people, that's Ethereum has expressed interest in adding support for the zero-knowledge proofs that I've talked about, which would be a way of adding these kinds of applications on top of it. And it's likely that altcoins will be able to experiment with these non-outsourceable puzzles, and if they can solve any of the issues with integrating them there, then it might be something that Bitcoin could eventually adopt.
How does Ethereum have to change in order to incorporate anything that we talked about?
The zero knowledge proofs, I mentioned that the verification takes, like 1.5 seconds for 100 of these. You can't implement that in the Ethereum programming language though, it would be much slower. So we would essentially need to just add an opcode to support verification. That's what would roughly be the approach for that. I think that Ahmed actually had at one point a working prototype of an added opcode into Ethereum that ran acceptably or something.
Yeah, we had this in a very simple opcode edition of
Okay.
Ethereum.
I was wondering, in the digital cash stuff that's involved here, there's presumably some D-logs involved. How secure are these?
Sorry, second?
There's some discrete logs involved or something that are, it's behind.
Yeah,
the-
like underlying signatures.
How
It's
big
even
are
a-
what's the bit size of these things now? 'Cause-
Greg, you know?
Which,
For the
Zero
Bitcoin's easy
Like,
to
let's say
say,
Bitcoin.
name Bitcoin.
I mean, there's been
Bitcoin-
such progress in discrete logs in the last couple of years.
Yeah, a lot of people actually talk about post-quantum cryptography here, so eventually the
Well, even
elliptic
forget
curve-
post-quantum, I
yeah,
mean,
just breaking the elliptic
just-
curves.
I mean, there was a 4800 discrete log done a couple days ago.
That was in a prime field, not in a elliptic.
Well, yeah, it was a prime field. It was
Yeah.
a discrete 3, but still. I was just curious what kind of discrete logs were used in Bitcoin, do you know?
I mean, it's using ECTSA, so it's this
Yeah,
particular
okay.
algorithm. The curve, yeah, the curve that's used is,
same in
yeah,
Ethereum.
it's a NIST curve, it's
the
not the
big-
most
it's the biggest
popular
NIST
curve.
curve.
Sorry?
Biggest NIST curve.
Is it the biggest? I don't know.
It's
the-
256 bit.
Oh,
yeah,
That's
the
with
signature-
128 bit security.
Oh, so I'm not going to invest in Bitcoin then. I mean, it's getting close, you know.
Yeah, I mean, the point is, right, the hash, well, I mean, the hash computation is 2 to the 70 for 10 minutes, and it's 2 to the 128 to break the discrete log, so.
Well, that's what they thought of this one that was just broken. They said it was advertised as 128-bit security.
Oh, really?
Yeah, because there's an elliptic curve, and then you multiply by, it was 800 bit.
I didn't hear about this actually. Who did it?
Menezes, Waterloo. Yeah, and it was multiplied by 6 to do the Bay pairing. And yeah,
Huh.
I just got the email yesterday.
One interesting a really interesting question is if it's so difficult to upgrade Bitcoin and the stakes are so high and it can't handle, service outage and so on. So is there a way to gracefully upgrade to the cryptography? And what I think works is that you can add new signatures, and then it doesn't matter if you crack old signatures as long as you don't have to upgrade the hash function, and the hash function is still secure. Then the log of what took place is, can be assumed valid.
Mhm.
So you could even gracefully upgrade the signatures, and only there's a feature that people are careful about, which is if you haven't spent money yet, you don't reveal what your public key is. You only reveal a hash of your public key. And this potentially prevents people from getting a head start on signatures, which they might be able to if they saw the public key.
And so the hope is soon in Bitcoin to upgrade to Schnorr signatures.
Okay.
Yeah, pretty straightforward upgrade.
Yeah.
Why is that any better?
More compact.
Sorry, say again what the
Schnorr signatures. You get native multisig, so you can do a smart contract between us two. If we play along and are nice to each other, then we just pay out to what looks like a one of one.
Schnorr signatures
address.
have like an aggregation
Yeah.
feature, so they algebraically combine really easily.
Sure.
Use a single
Strong
challenge
metrics.
value and then respond to that one challenge, so it reduces the size for a bunch of signatures on the same message, which you can't do.
It was patented until 2008, which is probably why Bitcoin didn't use it.
Yes.
This is kind of orthogonal to your thesis, but if you adopt a proof of work model, are there privacy concerns with that? Like, say I'm winning a lot of the block reward, and I don't want to divulge that I have so much at stake inside the system.
Yeah.
Is that a privacy concern that exists?
I think so. It's definitely not something that I model. It would be reasonable to, first of all, most mining pools advertise, they put a little message in blocks that they find saying, claiming it, so that's how you could build that kind of pie chart like I showed you. You could, if you wanted to, the members of mining pools, though, are effectively behind the shroud of the mining pool that they're operating in. And if you wanted to, you could just generate a fresh address every time you mine. So I don't think there's anything that makes you private, and whether or not you should be private and why you should matter, I don't think so explored, but I think that's interesting. That's my.
Is there a Pandora's box with enforcing privacy, that the moment that you start enforcing it strongly, that people with power can maintain that power and increase their power and do bad things because they're able to do it privately?
Yes, it's already possible even using Bitcoin, if you're very careful about it and diligent about it, to use mixes and various techniques of hiding your tracks. So, one heuristic is to say, well, this is still better to, improve privacy because criminals already get the benefit of privacy. It's just right now, people who don't go out of their way to do it, are leaking their information.
I guess I'm thinking of things not even, lots of the time privacy concerns are motivated by stuff like, anonymity and repressive regimes or something like that, but I'm thinking of the thing that lots of liberals are really excited about, which is income inequality,
Yeah.
where big corporations have tons of power and they just continue to distance themselves from normal people, and that a huge successful network like Bitcoin will just enable them to do that even more and not be, and be able to deny that they did anything.
That's a really important question that people are talking about in this community a whole bunch. My view on that is that this doesn't change any of the ordinary roles that existing social institutions are supposed to play. So what the technology allows you to do is to choose as a user whether you're going to be private or not. It's totally reasonable for a company in a regulated business environment to have to disclose, to have like a handful of like published keys where they receive all their invoice payments and be able to reveal to auditors what they use. And you can still do that even with the privacy preserving things. You can reveal, and if you fail to reveal all the inputs that came to your address, then you get audited and shut down or whatever. So it does, just like cash, provide the technical ability to not reveal where your income sources were, but in a regulated business environment, the big players could just as much be required to.
I guess I feel like it's a bit of, so I understand what you're saying, but it's a bit of an evasive answer to say that it's the same social institutions. I mean, the reason that before Napster we didn't care about people making copies of tapes was that scale was, not an issue. But the moment that you had the internet and you had this decentralization of copyright infringement, then all of a sudden it was costing big dollars, right? So the same thing is true. You can't easily ship pieces of paper all over the world, but you certainly can push around lots of transactions on Bitcoin.
Yeah, absolutely. I don't know. That is a good question. I don't have a further rebuttal to that.
So I guess if the audience doesn't have any more questions, can leave and we can, committee can stay behind.
Waterboard.
What's that?
Waterboard in private.
Andrew, do you want me to turn this off or?
Yeah. Okay. Thank you all.